A circular metal ring, as shown on a diagram below, is constructed so as to expand or contract freely. In a region with a constant magnetic field B0 oriented perpendicular to it, the ring expands with radius grows with the time, as R is equal R initial inside the bracket 1 plus alpha t squared. As the ring expands, grows thinner, its resistance per unit length changes according to the R is equal R0 inside the bracket 1 plus beta t squared. Find the current induced in the ring as a function of time. To check your answer, suppose, okay, so everything is given. So basically we have to find induced current. Okay, induced current. Okay. Before starting, I think we have to clarify a few things. The one thing is that the area of this ring is defined by a formula which is pi r squared, correct? Then the resistance is basically changing by the length. As length gets bigger, R gets bigger, so R times L. Now, the magnetic flux is equal to the B times A, right? Or in other words, B pi R squared. Okay. Then we have EMF. We're just taking the model of that one. Okay. EMF is equal d magnetic flux divided by dt. Okay. What else? Now let's start plugging the numbers. So B initial is a constant, so magnetic field is constant. So B and pi is also constant. Then dr squared over dt. Okay. Then we know that our R is given. So that means we can say that it's B pi. Now D inside the bracket. Okay, just a moment. R initial 1 plus alpha t squared over dt, right? Then if you continue, then what we'll get? We'll get B pi R initial squared, then multiplied to a 2, then we're taking derivative with respect to R, okay? And then we got 2, then 1 plus alpha t squared times 2 alpha t, right? What else? Then we have to take 2 pi r squared. Yeah, so basically we got initially this one, then we took the derivative with respect to time, okay? Not with respect to R. With respect to time, that's what we got it, to alpha t. Then after that, what we have to do now? So if that's the case, then we can say that it is equal to the 4b pi r squared alpha t 1 plus alpha t squared, okay? So far we got now EMF, induced EMF. Then after that, we know that induced current is equal EMF over R. Now since we said that R is changing with L, so R times L, so what we'll get? We get EMF, R is equal to the R. Now the length is equal to the, so length will be equal to the 2 pi R, right? So that means 2 pi r. Now let's plug the EMF into here. So we'll get 4b pi r initial squared alpha t 1 plus alpha t squared, right? Now the r in our case is equal to what? So the r in our case is equal to the r initial 1 plus beta t squared and 2 pi, and r was equal to the r initial 1 plus alpha t squared. Okay, so as you can see here, 1 plus alpha t squared will cancel with this one, r initial will cancel with 1 over the r initial, pi will cancel with pi, and 2 will cancel with, we have 2 here. So what is left? So the current is equal to the 2b r initial alpha t divided by the r initial 1 plus beta t squared. Okay. So let me check if everything's fine and if I didn't do any mistake. Okay, so it seems fine. So if you plug the numbers, I think you should get hopefully the right answer.